So this lecture will cover chapter 23 of the textbook, some of the major trends in evolution. So when we look at the world we live in today, we can see evidence of the process of evolution. For example, in the middle of a desert, we can find the remains of extinct whale species that let us know that, one, whales have changed over time, and two, the Earth itself has changed over time, because where there once were oceans, there now are deserts. And so we can find evidence of change wherever we look. So we can see in the fossil record evidence of macroevolution, as we've learned before, those big, broad changes above the species level. So we can see big things in the history of the Earth, such as the evolution of terrestrial vertebrates, such as reptiles and amphibians and mammals and birds. The impact of mass extinctions on the planet, we can see that in the fossil record, as well as the origin of certain adaptations like flight in birds or the jaw structure of mammals. We can see these things by examining the past. And one of the key ways that we understand the past is through the study of fossils. And I myself did research on fossil plants from the Cretaceous period for my master's degree. And we can learn a lot from fossils. So some fossils look like this right here. This is a plant from around the, I don't know, 400 million years ago or so. And that one is just sort of like flattened on a rock. But we can learn about the basic shape of plants by studying fossils like that. Other plant fossils, such as petrified or permineralized wood, you might actually be able to cut that and examine it in a microscope and actually see the cellular structure of this organism. And of course we get dinosaur footprints fossilized. We get bugs like this mosquito preserved in amber, where we can see its shape and structure and see that it has different features than modern mosquitoes. And we even get mummies, mummified organisms like this frozen wolf pup from Canada. So that would be a much more recent fossil than, let's say, those plants at the top. But we can get different kinds of fossils preserved in lots of different ways. But of course, to be fossilized takes some special requirements. Organisms have to, one, have, typically, I'm going to just say typically, they have to have hard parts that can fossilize easily, because soft parts usually rot away. And they have to have the right kind of burial or preservation. So they have to be in an oxygen-free environment, usually. And usually this involves being buried in some kind of water. Okay, so water and sediment. In fact, the kind of rocks we find fossils in are called sedimentary rocks. So sedimentary rocks are rocks formed by sediments from like the bottoms of lakes or the deposits of rivers and things like that. And that's where we find most of the fossils that we find. So one thing I want to point out is that the fossil record is incomplete, because most critters don't fossilize. Most of them rot away before they're preserved. Many fossils are destroyed as the Earth changes and rocks are crushed and heated up and melted and things. And then, to put it on top of that, the organisms that have fossilized, that have not been destroyed, still have to be found by humans. And we only see a certain portion of the rocks on this planet. Usually when we like cut a new road or something, do we expose rocks and find new fossils. So the fossil record is incomplete, and our knowledge of the fossil record is incomplete. But the fossil record is also biased, meaning the things that we're most likely to fossilize and we're most likely to find fossilized are those things that existed for a very long time, meaning they left tons of fossils. They were abundant and widespread. Once again, they're likely to leave fossils, and they have hard parts that are likely to fossilize. These are the things that are most likely, these kind of critters are the ones most likely to be fossilized and found. Now, that doesn't mean that things that were soft don't always get preserved, but they're much rarer and much harder to find, and we haven't found as many of them. So our record is biased for those things that were around a while, that were all over the place, meaning they fossilized in lots of places, and they had hard parts that were easily fossilized. Like teeth, for example, and bones and wood. Those are the kinds of things that are easily fossilized. But let's say we do find some fossils in some sedimentary rock. Then we have to figure out who they are, for one, and we do that by their shape or their anatomy. We also have to figure out how old they are. And how in the world do we do that? Well, first things first, we can do it by their relative ages. So we talked about sedimentary rocks. Sedimentary rocks are deposited in layers. And one of the early laws of geology was the law of superposition. And the law of superposition, so let's say there's a fossil here. We'll put X and Y. Which fossil is older, do you think, in this wall of rock? Well, the law of superposition states that older layers are below younger layers. So this rock layer was put down first, then this one, then this one, then this one. So in this layer, X is older than Y, okay? So that's what we call relative ages. We can tell if some fossils are relatively older or younger than others. That doesn't mean we know how many years old they are. We just know that, hey, this one was buried first before that one, okay? But then in more modern science, we can actually look at radioactive isotopes. So these are those atoms that release subatomic particles and they decay from one form to another. And they're found all over the place. And we can use different radioactive isotopes and determine the ages of a rock because these isotopes decay at a constant rate. So if we know that rate and we can look at that isotope in these rocks, we can figure out how old those rocks are. So each isotope is known as a half-life, which is the required time for half of the parent isotope to decay. Okay? So for example, if I'm just going to make up an isotope, okay? And let's say its half-life is 1,000 years. Okay, so half-life, 1,000 years. So when those rocks were first laid down, or when that organism was first dead, it had 100%, or 1 over 1 of that parent isotope. 100%, right? That was when that thing was first laid down. 1,000 years later, it'll have half of the parent isotope. Okay, what's half of a half? 1,000 years later, it'll have a quarter of the parent isotope. And what will happen is we'll start accumulating parent isotopes, or we'll start losing parent isotopes and we'll start accumulating daughter isotopes. So whatever that parent decays into. And we can look at the fractions between parent and daughter isotopes to figure out how old the rocks are that a fossil is preserved in. So here's an example of that. Originally we have 100% parent isotope. Okay? And then one half-life later, however long that is, it could be 1,000,000 years, it could be 1,000 years. It depends on what the element is that you're looking at. They have different half-lives. So in this example, here's one half-life later. There's half of the parent isotope, and now we have half of the daughter isotope accumulating. So the daughter isotope is what you get when you lose subatomic particles from the parent isotope, okay? Like some forms of carbon-14 decay into like nitrogen, I forget, another form of nitrogen. So you look at the ratio between carbon and nitrogen and you figure out how old that rock is. So after 2 half-lives, so that means you've lost half the parent isotope here, then you've lost it again, another half of it here. So now you're down to a quarter of the parent isotope. Then after 3 half-lives, you're down to an eighth. And after 4 half-lives, you're down to a 16th of the parent isotope. So you can do the math here. If once again, if this is a specimen that has if this element has a half-life of 1,000 years, let's say, then one half-life is 1,000 years. There'd be half of it left. 2,000 years later, there'd be a quarter of the parent isotope left, right? 3,000 years, there'd be an eighth left. 4,000 years later, there'd be a 16th left. So you can do the math pretty simply to figure out how old a specimen is based on your knowledge of the half-life and how much parent isotope is there and how much daughter isotope is there. So that allows us then to date rocks within, a few thousand years of accuracy at least. And that has allowed us to then figure out that the Earth itself is around 4.6 billion years old, or 4,600 million years old if you want to think of it that way. And we've been able to divide the Earth up into different times, different eons, eras, and periods to help us keep track of what was going on the planet and when different groups evolved. And we'll talk more about that in the next video.